Welcome everyone. Welcome to our linear regression session. In last session, we had built a multiple linear regression model, and we discussed that when we are building a multiple linear regression, we should observe adjusted R-square as a model performance measure rather than using R-squared. Both of these are very closely related to each other, adjusted R square and R square. As the name suggests, adjusted. There's some adjustment which is done to the R squared so that we get a much more reliable estimate. Now, what is that adjustment? I'll try to explain through a simple example. What happens is when we are building a linear regression model, as we keep increasing the number of variables, it is typically observed R squared will keep increasing. So this is our multiple linear model, which we did in our last session. On the income expense data, we have expense as a function of income, family members, EMI. And you can see that these variables are very closely related to each other. What I mean is dependent variable is very much appears to be a function of the independent variable's income. Expense of a household will increase if the income, they are having a good income. More family members, expense is likely to go up. And if they are staying in a rented apartment or having EMI expense, the expense, monthly expense will be on the higher side. So these variables seems to be very logical. If I run this code, I see my R square is 0.698 and adjusted is 0.678. First, I'm trying to explain the concept. Okay. Now what we will do is, to this data set, income expense, on which we build the model, we are going to add a variable serial number. So what I'm doing here, you can see this income expense data has 50 observations. To this income expense data, I'm going to add one column serial number. Currently serial number is not there. When I execute this, a serial number column will get added and each row will get a number 1, 2, 3, 4, 5, 6 like this. Shift enter. I have added a column serial number and here a column serial number 1, 2, 3, 4 has got added. It is very logical that expense should not be related to this serial number column, because this serial number is just a row identifier column which we have added to the data frame. However, despite knowing that serial number is not related to income expense data set, it is not related to monthly household expense which we are trying to predict. Despite knowing that, I'll try to build a model monthly household expense as a function of income, family members, EMI, and a serial number. What is important that we have to remember? What is the R squared of our previous model? The R square of our previous model is 0.69 and adjusted is 0.678. With the serial number variable being added, what is our R squared? Control enter, executing the code. If you see, I have wrongly typed here. This should go up. Control C. The adjusted I have written as R squared and R squared I have written as adjusted. My mistake. Control V. Okay, once again let's run it. If you see, the documentation says the model R squared is, and here I was showing adjusted earlier. The model adjusted. Here we should have adjusted. Okay, let's run once again. Okay, now the output is correct. So the output, you can see the model R square has now come out to be 0.70. What was our R squared earlier? Our R square earlier was around 0.698. Earlier R squared was this much, and earlier adjusted R squared was around 0.67. If you see, by adding a serial number, my R squared has increased. However, adjusted R square has decreased. I need the third decimal place also. Adjusted R square, third decimal, 0.678. Yeah, 0.678. Compare 0.678 with 0.675. The point is, as we keep on adding variable to a model, so as I am trying to predict expense with more and more variables, earlier we had only income, simple linear regression, we had only one variable. Our R squared was 0.42. We increased and brought in a relevant variable, number of family members. Our R squared increased from 0.4 to 0.58. I added one more variable, EMI, it increased to 0.69. Now I added a variable which is actually a junk variable. Despite adding a junk variable, my R squared has increased. But the moment I add a junk variable, you see, adjusted R squared has actually decreased. So what happens is, adjusted R squared is a penalty that we add to the model. Because of that penalty, it brings down the R squared value. If you add a variable, if you add a predictor variable to predict the target phenomena, which does not have any correlation and which does not really make sense, you may see adjusted R square falls down, and because adjusted R square goes down, by comparing it with the previous adjusted R square, you can come to a conclusion: the variable added does not contribute to the model. If the adjusted R square increases by addition of the new variable, then it means the variable might have some correlation and it may have some sense. It may make some sense. However, if it decreases, it sure short means the newly added variable is of no importance. As such, you should remove it from the equation. Now comes the equation. Adjusted R square equation is 1 minus of 1 minus R square into n minus 1 divided by n minus k minus 1. So here, what is n? N is number of observations, k is number of variables. As you keep on increasing the number of variables, this factor, this 1 minus and 1 minus of R square, it will try to reduce the overall value of adjusted R square. Okay, and it will reduce specifically when the variable being added does not add value to the equation. So what I'm doing now is, quickly I'll run this code once again. Control X, this part of the code, control enter. Okay, there is a slash here, plus here, control enter. 0.42, note R square and adjusted 0.42, 0.40. Control Z, Control Z. Okay, now I reduce the number of variables, increase the number of variables. Redone 0.42 and adjusted, both of them is increasing. Control Z. This time around I'll remove serial number, because these variables which are being added one by one is adding value to the overall equation. So you see R square is also increasing, adjusted R square is also increasing. Now I add that junk variable once again, serial number. These are the numbers 0.697 and 0.678, and this time R square has increased, but adjusted R square, because it penalizes the model if a junk variable is added. That's why adjusted R square has gone down. The moment adjusted R square has gone down, you should make a conclusion. The variable which was added did not contribute to the model. So this is a simple concept of adjusted R square, and this is the formula of computing adjusted R square from R squared. The codes are all given and the interpretation is given here. So with this, we have understood the concept of adjusted R square. Now comes more interesting concepts, challenges, which is multicollinearity, the phenomena of multicollinearity in a linear regression model. So let's get to multicollinearity. What is multicollinearity? How is multicollinearity identified? And how do you remove multicollinearity from your model? I hope all of you have been able to execute the code by adding serial number. If not, what I'll do is I'll just quickly show you the serial number syntax and make necessary change in your code and execute it to see the output. This is how we add the serial number column to our data set. Okay, let us now learn what is multicollinearity, what is variance inflation factor. In simply put, multicollinearity is a phenomena when two variables, two or more variables, or let me be more specific, when two or more independent variables are highly correlated with each other, it leads to multicollinearity. Very simple example. You have a particular task to be completed, and that task is going to take, say, 4 hours. You have 3 capable person in your team who can do that task, and all these 3 people have the same skill set. Will you put all the 3 people on that task, or you will assign that task to one person? Obviously you will assign that task to one person, because there is no point all 3 working on the same task. Now applying this logic to our linear regression. You have the target variable. In our case, it is expense. We are trying to predict expense. Now to predict the expense, we have a variable monthly income. There is another variable which is annual income, and the annual income variable is highly correlated to monthly income. We saw the correlation, it is around 0.97, which means I can calculate annual income from monthly income, and the data set, the way it is been given to you, annual income is roughly equal to 12 times monthly income. So to predict the phenomena expense, I really don't require monthly income and annual income, both the variables as part of the equation. If you have both the variables coming in the equation, it is going to lead to a problem called multicollinearity. Now, why multicollinearity is considered as a problem? When you have multicollinearity problem, which means there are two or more independent variables highly correlated, and all of those highly correlated variables being considered as part of your explanatory variable to predict the dependent value variable, it leads to certain challenges, and those challenges are the estimates, beta estimates of the independent variable may start showing erratic behavior. Now, what do you mean by this erratic behavior? They may show up with wrong sign. The relation may be positive correlation, but the beta may come negative. Let us try to understand this with some code execution. Let us first build the model. I'm not taking the serial number. I'm just executing this code. Control enter. We already built this model. I'm just rerunning it. Now, certain things, when you see this entire summary, the first thing you have to see the variables which are significant, and we have already discussed which variables, how we see significant. All these variables are significant. The second thing is that you have to see the coefficients. We already discussed the sign of the coefficient. Now here, the monthly household income, the sign of this coefficient is positive. Now why it should be positive? Because the correlation between monthly household income and monthly household expense is a positive correlation. As such, the beta should be positive. Similarly, the correlation between expense and family members, more family members, more expense, less family members, less expense. So there is a positive correlation. So the beta should again be positive. Likewise, if a family is staying in a rented or a EMI apartment, in that case there is more expense. So their monthly expense will be on the higher side. So there should be positive correlation. If the correlation is positive, the beta coefficient should come positive. And all of these are coming positive. So far, everything is okay. Everything is in line with what we think. But now what we are going to do is, we know this is monthly household income. It is highly correlated with annual income. Let us build the model by bringing in the annual income variable also. We are now bringing two variables. The definition is two or more. So here I've got two, which are highly correlated. These two are highly correlated. What is the correlation? We have already seen here. This is a syntax. We have already seen earlier the correlation. So let me just take this syntax again below. So it refreshes your memory. We have the correlation between monthly household income and expenses 0.97. Now with this correlation, I am taking both variable in the model and run it. Control enter. Let us see the beta coefficient. Here I've just printed the parameters, the beta coefficients. Monthly household income, beta is positive. Income with expense, positive correlation, beta should be positive. Similarly, we have beta coefficient of family members positive, EMI positive. Annual income is coming negative. Logically, if a family's annual income is high, that family's monthly expense should also be on the higher side. But here annual income is coming negative. If I simply remove this part of the variable, this variable, now this time what I'm doing is I'm removing monthly income and only keeping annual income. Annual income beta has become positive. If I add back this and now remove this, monthly income anyways was positive earlier also, but I now add annual income again. Monthly income remains positive, but annual income becomes negative. If monthly income is there, annual income becomes negative. But if monthly income is removed, annual income comes with a positive correlation, positive beta coefficient. So there is some problem which is occurring in our beta coefficients of this predictor variable. Why it is happening? Because the definition says a phenomena where two or more independent variables are highly intercorrelated, which means one variable can be predicted from other. Can I predict one variable from other? Can I predict annual income from monthly income? Yes, I can. The moment I say I can predict one independent variable as a function of other independent variable, I end up in a multicollinearity problem, and one of the impact of multicollinearity is the sign may not come proper. The beta coefficients may not come proper. Another important impact of multicollinearity is significant variable becomes insignificant. Variable which was statistically significant end up becoming insignificant, which means it appears as if the variable does not have explanatory power because of multicollinearity. Let us once again see. This time around I'll do the entire summary. So the summary syntax, I'll remove this annual income variable so that you can again connect what I'm trying to say. Control enter. The p value of monthly household income. If you see this, the p value is 0.000, which means the variable is statistically significant. Now I add back annual income. Monthly income, which was statistically significant, is now significance has gone down. Earlier it was 0.000. If I consider, and typically so long as you are considering alpha threshold of 0.05, this variable is still significant. However, many of the models are built at a alpha threshold of 0.0001. 0.0001 means 99.99% confidence. And many of the commercial models in industry are typically built using a alpha threshold of 0.0001. If I use a criteria of alpha 0.0001, my monthly household income variable has become statistically insignificant. The point I am trying to make is, because of multicollinearity, our variables act erratic and their beta coefficient sign changes. Sometimes it becomes plus, sometimes it becomes negative. The variable significance also goes off. The variable which was significant becomes insignificant. So how do you handle multicollinearity? To handle multicollinearity, it's very simple. The variable which is correlated, one of that you have to drop off. Now in this case, the two variables are so self-explanatory that we can quickly identify that these variables are highly correlated. As such, we have to drop one of them. However, this will not be the scenario most of the time. There will be many practical scenarios where you are going to handle hundreds of variables, and in hundreds of variables it may not be easy for you to identify which variables are highly correlated with each other, and as such you cannot simply drop them. So there is another concept called variance inflation factor. But before I get into this variance inflation factor, I need to slightly explain this concept with more detailing. So what I'm now going to do is I'm going to take this equation dot params, control enter. So this is our intercepts. So let me copy this, control C. This is the Excel that we were working. So let's add one more Excel and rename it multicollinearity. Control V, the parameters which we got. So data, text to column, it's delimited by space. Okay. Yeah. So what is the equation format of this parameter? The equation is expense is equal to intercept. Intercept is minus 5331. So let's write that minus 5331 plus 0.417 times, I'll just write monthly income as MI, plus 3248 times family members, I'm just writing FLY, plus 0.658 times EMI or rent, I'm just typing EMI, plus bracket because it's a minus symbol, so minus 0.017 times annual income, which I'm saying AI. So this is actually the equation which we have got. Okay. Okay, I have written here some code of dropping certain rows. So what I'll just do is I'll comment this part, and instead of writing it like this, we don't want any rows to be dropped off for the concept which I'm trying to explain. So I'll just remove this drop and again take the equation. Okay, control enter. Yeah, so let me take this 5124. This is the equation. So I can copy this once again and update. Control V, data, text to column, finish. Yeah, so I've updated it and the equation also will change it. 5124 plus 0.409 plus 3224 plus 0.56 and minus 0.016. Okay, I have updated this, and let me also show you the summary. There were certain rows which I dropped. Now when you see the summary, here you see the monthly income has become more insignificant. 0.012 is again insignificant. Yeah, so this is the code that we are running. Okay, now what we are going to do is we'll remove this annual income and run it, and once again take the params. We require the params. We take the params, copy, come to Excel. This is the second equation. Data, text to column, finish. So this is our second equation. Now without annual income, this is my equation, and that equation looks like something. Expense is equal to minus 5148 plus 0.210 times monthly income plus 3232 times family members plus 0.685 times EMI. With multicollinear variable, this equation is without multicollinear variable. Now we know in our data set, annual income and monthly income are correlated to each other, and the data set, the way it has been given to you, is having annual income very close to 12 times monthly income. So if you see this data set, sorry, yeah. So if you see the data set, if you just observe 5,000 into 12, 60,000, 6,000 into 12, 72,000, the 10,000 into 12, 1,20,000. The variables are designed such that it is almost roughly 12 time multiplier. What I can do is, in this equation, where annual income is there, I can replace annual income by 12 times monthly income. If I replace annual income by 12 times monthly income, this equation will become 12 monthly income. We need to compute what is minus 0.016 into 12. So let us do that. Minus 0.016 multiply 12. This is 0.192. So I can rewrite this equation as minus 0.192 times monthly income. However, I have got 0.192 monthly income and I've got 0.409 monthly income. So we can do 0.409 minus 0.192 equal to, that is 0.217. So this equation can be rewritten as 0.217 times monthly income, and this component goes off. Now I take this equation from here and just copy paste it here. Compare the two equation. If you just compare the two equation, you can note the two equation is virtually the same. These two equation are virtually same. There's not much difference between them. What happened? We had two correlated variables. The regression was trying to give beta estimate to both of them. As such, it was just trying to do a balancing act, and in this balancing act the beta was getting distributed, and because the beta was getting distributed, one of the beta was becoming positive and other was becoming negative, and in the process the variable was also appearing to be insignificant. So we don't require both the variable in the equation, as one can be expressed in form of other. We don't require both of them, and it is very important when you build a linear regression model, you cannot have multicollinear variables in the model. Now the challenge is, how do we find this problem which we took is very simple, where we have upfront knowledge of variables which are correlated to each other. When we solve complex problems, we may not have this information upfront available with us. In that case, how do we solve multicollinearity? The way to solve multicollinearity in that is to find the variance inflation factor. So we now come to another concept, VIF. VIF is used to find multicollinearity, whether multicollinearity exists in your data. As spoken earlier, VIF is the test for multicollinearity. The formula is just given below. Now, how is VIF computed? Let us assume you have 4 independent variables, x1, x2, x3, x4. Now, if I just simply see x1 with x2, I can say x1 is correlated to x2 or not. I can compare x1 with x3. I can compare x1 with x4. However, there is a possibility that you can predict x1. You can express x1 as a function of x2 and x3. Or you can express x1 as a function of x2, x3, x4. For example, in the same example that we just took here, annual income. Here in our case, the annual income was very simple, was equal to 12 times monthly income. However, many people, annual income is not simply a 12 times monthly income. It may be plus annual bonus, plus there may be a sales commission, because there are many people who have a monthly sales commission, plus company performance, variable payout, how good the company overall has done. Now, in this case, if I have monthly income data, I have each person's annual bonus information, I've got sales commission information, I've got their payout that they have got as a company performance variable payout. If I have all of this, in that case, annual income could not have been simply replaced as 12 times monthly income. But annual income column could have been computed as a function of monthly income, annual bonus, sales commission, company performance. But individually, if I try to see correlation of annual income with monthly income, or individually I try annual income with annual bonus, or individually I see annual income with sales commission, individual correlation may not come very high. In that case, we may not be able to capture multicollinearity if we are simply going with correlation of one variable, one independent variable with other. So we need to see multicollinearity by checking whether one independent variable can be expressed as a function of other independent variables. So the way it happens is, coming back to this, assume you have 4 independent variables. All of these we don't have to do. All of this automatically happens in the software like a Python which we use. So what happens in the background is you regress. You are actually building a linear regression of x1 with x2, x3, x4. Then you compute what is r squared. We know r squared, square root of r square is correlation. Okay, we already know. So which means we can compute x1 correlation with all these variables taken together by taking a square root of this. But we really don't need to get into correlation. We first regress x1 with x2, x3, x4, get the r squared value of this regression equation, and compute VIF by this formula, the formula which is given in a bigger font above this formula. So here we compute then what you are going to do, when I say you are going to do, it means the software, then you regress the second independent variable with the other three independent variables. If you have 100 other independent, it will do regression of x2 with 100 other independent. Again, you will get r squared. You apply that formula and get the VIF for x2. Then you will regress x3 with other variables. You will get the VIF of x3. You do x4 with other variables, you will get VIF of x4. This way, for each variable, each independent variable, we regress with other independent variables, find R square, using the VIF formula, find VIF. I will get VIF, variance inflation factor, for x1, x2, x3, x4. And there is a table of how to read VIF. So when you run the code, you may get such an output. Let's run that code. As I mentioned, we typically don't do all of these manually. So there will be some logic, some function available. Here there is a VIF code which is given upfront. Here I have simply said I am trying to build a model where I have these variables. I'm trying to build a model of I'm saying I'm trying to build a model of expense as a function of these variables. So these are my 4 independent variables. So the function will automatically understand which are independent variables. It will run a regression between them and give you a VIF. So let us just quickly run this. I get a VIF table. Now, how do I find out whether there is a multicollinearity or not? If any variable has got a VIF value above 2, there is a multicollinearity. And here we can clearly see monthly household income and annual income, both of them has got a VIF above 2. Because the VIF is above 2, which means my equation has got multicollinear variables. And if there are multicollinear variables, I have to remove multicollinearity. The rule is remove one variable at a time. You do not remove all variables in one go. So there are two variables which have got a variance inflation factor above 2. One of them has to be selected. Thumb rule is select the variable which has got the highest variance inflation factor. So here I have got 17.7 for monthly household income. So I should be dropping monthly household income. The second thumb rule is you apply your business logic also, business judgment also. Now business judgment tells me I am trying to predict monthly household expense. Then logically, why should I drop monthly household income? I should drop annual variable. Because the VIF are very close to each other, I will drop annual household income. If I drop annual household income and run this code once again, the moment I run it again, you can clearly see that this time around the VIF of no variable, none of the variable is above 2, which means multicollinearity has been handled. So this is how you typically handle multicollinearity, how to remove multicollinearity, the entire steps. Any variable having VIF above 2 is considered to be multicollinearity. Drop one of the variable. Do not drop all. Drop one. You should drop one variable at a time. Again iterate. After iteration, once again check. Is there any variable having VIF above 2? If there is, once again, the thumb rule is drop highest VIF variable. However, you may choose to select the variable based on your business judgment. Once again, you drop the variable which has got VIF above 2. Keep iterating till VIF of all variables is below 2. So this is a very simple approach of identifying variance inflation factor and removing multicollinearity from your equation. Final note, I already explained why we do not use correlation to detect multicollinearity. Reason is correlation metric shows correlation between two variables only. It will take x1 and x2. However, the definition of multicollinearity is when one independent variable can be predicted from one or more independent variable. This essence of one or more is captured in VIF, but it cannot be captured in correlation. As such, VIF is a better approach to detect multicollinearity rather than using simple plain correlation. So in this part of the session, we have learned how to find multicollinearity and how to remove multicollinearity. What are the challenges of multicollinearity? All of that has been discussed. Those watching the video online, I have just paused here for a while so you can type in the code, get the output and check your output. So this is the syntax. I'll run one again with annual variable, control enter. So this is the output. Okay, we now move on to the next topic, variable transformation. So we have just completed multicollinearity VF. Our next topic, agenda, variable transformation. Now, what is variable transformation? First, we have to understand this concept. We are trying to build a model where we are trying to predict expense as a function of independent variables like income, number of family members, and so forth. However, in linear regression, one of the basic assumption is that the relation between the dependent and the independent variable, as I'm trying to show, is linear. Either it is a positive correlation, positive linear relation, or it is a negative relation. Either of them, but the relation has to be linear. At times, you may not have the relation perfectly linear. You may have a relation, something which is like this. What you can see is up to a certain point, it was going up, and then there is a plateauing. Now, if you try to build a linear regression with this, and you try to fit a linear regression on this trend, what may happen is it may fit a trend, but the trend, it will fit something like this, the blue colored line which I'm trying to show, which means here it is underfitting. In this zone, it is going to underfit. Here it is going to overfit. Let me change the color once again, which I'm now taking as a green color. In this zone, it is going to overfit, and here again it is going to overfit. Is there a way by which I can transform my original variable, the independent variable, such that the relation between the dependent and the independent becomes more linear? And it is possible by applying various kind of transformation, and there are some of the various transformations which we regularly apply is natural log. For example, this one which I showed the example could have been solved by applying a natural log transformation. Or there is other transformation called exponential, square, square root, inverse, binning, bucketing. So there are certain standard transformations which are regularly used, and one of the most commonly used transformation which most of the time gets applied is a log transformation, that is natural log transformation, log to the base e. By just applying this basic transformations, what you can do is you can achieve significant improvement in model performance. As such, knowing this concept of variable transformation is very essential, and this is what we are going to discuss in this part of the session. So let us try to understand variable transformation. In machine learning, we apply variable transformation to improve the fit of the regression model on the data. So whatever is the target phenomena, to improve our fit of our model, we apply certain transformation. Now, while applying variable transformation, what is very essential is you visualize, you see the trend between the dependent variable and the independent variable, and you also see the distribution of the independent variable. And that's where we had this one important thing that we were doing, pair plots. We did this entire pair plot. The objective of this pair plot was to see the distribution, and here you can see the variable, the fourth variable, this one, EMI or rent. We see this is not normal. If you see this, the distribution of all other independent variables diagonally, if you see all the distributions diagonally, more or less most of them are normally distributed. However, EMI or rent is highly skewed, and the trend of EMI or rent with expense also is not having a very good linear relationship. Which means if I am bringing this variable in the model without transformation, I may not get a good fit. If I can do some transformation, I can probably improve the fit of my overall model. Now, what kind of transformations we can apply? We already discussed there are various standard transformations, and log is one of the most used. So here I'm going to focus on the EMI rent variable. The plot here shows that the distribution is a skewed distribution. Can I convert this skewed distribution to some normal distribution? Probably yes, by applying log. So let's get into our Jupyter notebook. Coming back to Jupyter notebook, we have done multicollinearity, and here we come to this. So first is the syntax to see the distribution. We are making use of histogram plot, and then we are giving all these parameter setting to make the graph much more visually readable, and or by giving the labels to x-axis, y-axis, and title, all of that. Control enter. I get this kind of graph. It shows that it's not normally distributed. And a variable which is skewed, to make it normal, one of the standard transformation is a logarithmic transformation. This is other way of making the plot. It's okay. These are all programming, not much to be bothered about. What is more important is the transformation. Okay. Before I run that, here, this is the code. We have R square of 0.69 adjusted of 0.67. Kindly note these two numbers. Our R square is, adjusted R square is 0.678. What is the transformation which we are going to apply? We are going to apply a logarithmic transformation. What is log of 0? Log of 1. Log of 1 is 0. But what is log of 0? This is the function log of 1, control enter, 0. But what is log of 0? Undefined. Log of 0 is undefined. My income expense variable, EMI variable, in the income expense data has values which is 0 or any number above 0. If I simply apply a logarithmic transformation on this EMI, I will end up into this kind of error. So let us just simply apply that transformation for now and end up into that problem. Control enter, I get this message. There is a divide by 0 which was encountered at some of the places. So we created a variable, logarithmic transformation variable, and we have ended up into this issue. I want to see that data set. Income expense, control enter. I scroll down, and on the right hand side I have to scroll. The cursor is very much on the bottom. Yeah, so here you can see there are many variables having minus INF. How do we avoid this problem? We simply add +1. So remember, whenever you are applying a logarithmic transformation and if your variable has 0, simple way out is add +1 to all the records. So if the EMI is 2000, what I'm saying is instead of doing log of 2000, do it log of 2001. Log of 2000 and log of 2001 is not going to be much different. I'll just show that. Control enter. 7.6 and 2001 will be 7.601. So there is not much difference. So for each value, we add a +1. The benefit of that is we will overcome this divide by 0 issue. So now I run this once again. My warning is gone. If I now see income expense data and I just scroll again, all those minus infinity which we had encountered, all of those have got replaced by 0. I can now use this variable. Fantastic. We have done. So let me just delete this. Let us see the distribution of this logarithmic transformed variable. This is the distribution. This big bar is 0. Ignore this big bar. Focus only on this much part of the graph. And if you see this part of the graph, it has become somewhat normal. It has become somewhat normal now. And if we go back to the previous graph of the same variable, this somewhat normal is actually this part, and this is nowhere normal. So by making this component, which I have put in a red color, is actually any value which is above EMI 0, and it is nowhere near normal. So by making a logarithmic transformation, I have made this variable to some extent normal also. One of the point in linear regression is if your independent variables are normally distributed, those variables, when they come with a good predictive power, when they are highly correlated with your dependent variable, they tend to improve the overall model. So if you have a significant variable and that significant variable is normally distributed, you will see the model performance will improve. Our EMI variable was not normally distributed. By applying a logarithmic transformation, I have created two segments, a 0 and a segment having any value other than 0, and that segment has now somewhat normal distribution. Now if we bring this variable in our model, what will happen? Let us build the model. So here I am showing you two models. This is my model 1, which has original EMI variable. This is my model 2, where I have got logarithmic transform derived variable transformation has been applied. I am having this. Other variables are same, income, here also income, family members, here also family members. I am going to see what is adjusted R square without variable transformation and adjusted R square with variable transformation. Control enter. I have created the variable, and this is my adjusted R square 0.678, and this is my 0.743, 0.7436 divided by 0.6781. Enter. There is 9.6 percentage, 9.7 percentage, approximately 10 percentage improvement in the model accuracy, model R squared. A very simple transformation has helped me increase the model performance drastically. So this is where the concept of variable transformation becomes very important while working in linear regression. So the point is, in linear regression, if the trend between your dependent and independent is not perfect collinear, can we transform the dependent variable so that the relation become more correlated, and can we make our independent variable more normally distributed? If we can do these kind of transformation, the model efficacy can be increased significantly. I'm going to still do one more transformation, one more basic transformation to show how I can further improve the model performance measure. In the meantime, let us execute these codes. So what I'm going to do is I'm going to scroll up and pause here, so you can copy paste. Those watching the videos, you can copy paste the, not copy paste, basically type the syntax, make the chart, pause the video here. Let me scroll now below, and after creating the variable, run this part of the syntax and compare your model performance measures. Is it possible to improve the adjusted R squared further using these variables only? Probably yes. If we see the graph of logarithmic transformed EMI variable, there is a bulk of observation which is at 0, and then there is other set of values which is between 6 to 10, 12 something. What it shows is there is two segments in our data. One segment who does not have any EMI or rent payout, and other segment which has got EMI or rent payout. Obviously, those who have got a EMI or rent payout might have to save some money from their regular normal expenses because they have to meet EMI or rent. And the other households where they do not have the EMI or rent, they have got extra money in hand, they may live more lavishly. So these are two segments. Can I try out building model by having this segment information? One approach is you split the entire data into two data set. One data set being EMI rent payers and other with no EMI or rent, and build separate models. However, the other approach is I can simply create a flag. So here what we are doing is we creating a flag where we will say if there is any EMI, I'm using a lambda function. In this lambda function I'm passing EMI, which means I'm representing this EMI variable by X. If there is any EMI going, then take the value 1. else take the value 0, we are going to create a flag. So this is my data set 1100. Now I'm going to bring this variable also in the model. Flag logarithmic transformation variable, my original income, family members, all of those variable. Control enter. Let us see the adjusted R square 0.758. What was earlier a R square? 0.7436 and now 0.758, this number. So I have improved the model, or probably what I can do is I can take this 0.75, I've forgotten the number, 0.758, 0.758 divided by 0.7436. Once again, let's see the improvement. There is approximately 2% improvement in the model. This way, if you see, coming from the original model, this without any transformation, if I compare with respect to that, I have already done more than 11%, almost 12% improvement in the model. As you keep improving the model, the scope of further improvement will keep diminishing and it will become challenging. But the point which I want to convey with all of these transformations and basic transformations is by doing variable transformation, we can improve the fit of the model, and it is a very important step in model development process. Note, in linear regression, there is no assumption that the explanatory variable should be normally distributed. However, the model performance is improved significantly by transforming a skewed independent variable and making it normal distributed. As a practice exercise, I would like you to work on the initial 3 explanatory variable, which we have already used, and see whether you can do any further transformation to improve the model. Besides those 3 initial variables, there are other variable highest qualified member and number of earning members, which we have not used in our model development so far. Can you try bringing these variables in the model? Check whether your adjusted R squared is improved. Can we do some transformation to these variables also? And while bringing in more variables and doing transformation, you should ensure you do not introduce multicollinearity in the model. In our next session, we will see how to use the model to predict the estimated value, how to compute error, root mean squared error, and how to build zero intercept model. Till then, thank you. Bye bye. See you in the next session. Just wait a minute before I conclude. One more point as an addendum to the session I would like to make. So let's just quickly see the summary of the model by adding this flag variable once again. So what is the summary? If you see the summary, this variable which we have added is coming with a p-value of 0.06. And if I consider threshold of 0.05, or as I said, we typically consider a threshold of 0.0001. With either of these thresholds, this variable is not significant. Should we drop? The answer is no. The reason is we have created 2 variables. One is a logarithmic transformation and we have created a flag variable. Both of the variables are coming from the same original variable. If I remove this once again and run it, you will see that the logarithmic variable is become significant. Moment I add it, you will see the logarithmic variable becomes insignificant. However, we as a analyst who is building the model, we know we created both these variables from the same original variable. As such, they are more likely to be multicollinear. And if they are multicollinear, they will have some impact on the p-value. Given that fact, I am not going to drop this variable. This is a call as a data scientist you have to take. And this is the area of variable transformation where your skill variable transformation is the art, the statistics, the p-values, the significance, the beta coefficients, that is a science. You have to have a fusion of your art of how you are varying the variables, how you are transforming the variables, bringing it into model, and how you relate the statistical output and then take a decision. That is an art which you will have to develop. Let me just quickly try to see the VIF output also. Even if the VIF output for this variable is going to be more than 2, I'm going to keep the variable. I need to copy paste that code. As such, I'm scrolling up. Yeah, here's this code. Let me copy it. Yeah, this is what we executed. So below that, let me enter, and here we will run it with our these two variables. Control V. I think so everything is done properly. Control enter. And here my VIF is 69.33 and 69.36. This is between the logarithmic transformed and the flag variable, which I knew will come as very high VIF. However, my judgment is there is 2 segments in the data, and to bring that segments, I'm doing a variable transformation and creating a flag variable. The expense of a household which is having EMI will be higher, and the expense of a household which does not have EMI will be lower. We have flagged those households not having EMI to be 0 and those having EMI to be 1, which means we have prepared the data having a positive correlation. The beta should have come positive. However, my beta is also coming negative. At the same time, I know I have introduced this variable as multicollinear. With this, the combined effect is giving me a better model, better R squared. As such, I will let both of these variables be part of my final model. Once again, I tell you, model development is art and science. It is the fusion of art and science. And while developing the models, you will repeatedly come across these instances where you have to take a decision. And that is where a, a good analyst, a good data scientist gets differentiated from an average data scientist. With this, now I conclude today's part of the session. Thank you and see you in the upcoming session. Bye bye.